Hi everyone, welcome to my channel. Myself Dr. Anil Devda, working as an assistant professor, Department of Chemistry, JSS Arts, Science and Commerce College, Gokak, affiliated to Ranichinama University, Belagavi, Karnataka. So today's topic of discussion is plane photometry. So we'll see first the syllabus according to RCU, Ranichinama University, Belagavi. So in the plane photometry, we are going to discuss principle of plane photometry, instrumentation, meaning the plane photometer, its working, what are the construction and so on. So next is limitations of plane photometry, and further we have two determinations, that is plane photometric determination of sodium and potassium. So we'll see one by one in the today's video. Well, so we must be knowing the plane test of the elements, so that we are always doing in the qualitative analysis in the fourth semester. For example, if we want to know the plane test of sodium, so we are just putting sodium salt into the flame and it imparts golden yellow color. Similarly, the other elements or other salts, other elemental salts, for example KNO3, potassium, so that imparts this color, and calcium, so on. So let us see, so what is the basis of these colors the moment we spill the salts into the flame. On this basis we have a technique, that is spectroscopic technique, for the determination of important elements in the various samples. Well, plane photometry is based on measurement of intensity of the light emitted when a metal is introduced into the burner flame. So it is totally based on the measurement of intensity of the light emitted when a metal is introduced into flame. So there are two parameters comes here when we talk about the emitted light. We have two parameters. One is what is the wavelength of the emitted light, and other is what is the intensity of the emitted light. So based on this, we can have qualitative as well as quantitative analysis of the elements present in a sample mixture. The wavelength of the light emitted, or I can say the wavelength of color, tells what the element present in the sample is, what the element is. So that is what is called qualitative analysis of the element. Then the color's intensity tells us how much of the element present in the sample, that is quantitative analysis. So plane photometry is more accurately called plane atomic emission spectroscopy. So we will understand this one in the principle of the plane photometry. So why we are calling it as atomic emission spectroscopy, that is plane atomic emission spectroscopy. So the very basis of this plane photometry is the intensity of the light which is emitted when a metal is introduced into the flame. So for example, sodium chloride is introduced into flame, or if you spill this salt into the flame, so this imparts golden yellow color is just because of the presence of sodium atom present in the salt. Well, we will see the principle. When a solution containing metallic compound is aspirated or spilled into a flame, the following changes occurs. So what I mean to say is, when I say solution, this means that so the salt which is present in a solvent, that is solution. Okay. The first, what happens the moment you aspirated this salt into the flame, solvent evaporates, leaving behind the salt in the flame. So we have a mixture, we have a salt in a solution, that is called a solution. So we have a salt in the solvent which is called solution. So this solution, that is an aqueous solution, is aspirated into the flame. So what happens next is, so the solvent evaporates first, leaving behind the salt in the flame. So this salt is in the flame. Then what happens later? The salt goes to vapor state, or I can say gaseous state, and the vapor state and in the vapor state salt dissociates into its constituent atoms. For example, the salt which is made up of two atoms, that is for example sodium chloride Na plus and Cl minus, which is in the gaseous state. So the moment we put into the gaseous state, the salt dissociate into its constituent atoms, that is M in gaseous state, that is the metallic part, and the other is the X part, that is X, which is also in gaseous state. Some of the gaseous metallic atoms gets excited by thermal energy, as we are talking about. These all process happens in the plane. So these gaseous metallic atoms get excited by the thermal energy of the plane to higher energy levels, or I can say excited levels. And the excited atoms which are unstable, which quickly loses energy in the form of photons and return to lower energy state or the ground state. So this whatever these excited metallic atoms loses energy in the form of photons, this is very important. This is we are going to measure in the plane photometric technique. So this is the principle of the plane photometric technique. The emitted photons imparts characteristic color to the plane, and the intensity of the color is a direct measure of the concentration of the element present in the plane. Examples: sodium emits sodium emits radiations at an wavelength 589 nanometer, and this corresponds to the flame color is yellow, that is golden yellow. Similarly, if you take the potassium, the emitted wavelength is 766 nanometer and the flame color is violet. Calcium, the emitted wavelength is, which imparts the color is orange and its wavelength is 622 nanometer. Barium imparts lime green color at an wavelength 554 nanometer. Similarly, lithium imparts red color, or lithium salt imparts red color at a wavelength 670 nanometer. So let us discuss little bit detail about this one. So when the metal atom in the gaseous state, in the ground state, we have the electron in the ground state. As soon as it absorbs thermal energy from the flame, the electron in the metallic atom in the ground state get excited to higher level, that is electron in the excited state, and this excited atom, or I can say excited level of this electron, makes the atom unstable. So this unstable metal quickly loses energy, and this again comes down to ground state or the lower state. So during this it loses energy in the form of photons, and that is light, which is having a specific wavelength. So here we can see, when the electron excited to higher level and the atom becomes unstable, the electrons immediately loses its energy in the form of photons with a specific wavelength to ground state, and this imparts specific color. That's what we can say. The excited atoms which are unstable quickly loses energy in the form of photons and return to lower energy state or the ground state. So this is a quick principle of the plane photometry. So here it comes. So here we have a solution of the salt solution, or I can say it is solution containing salt, So here, when we aspirate this salt solution into the flame, so this aspiration meaning we have a solution which containing fine particles of the solution, that is we call it as aerosol or mist. So this mist present in the flame, and this evaporation takes place in the flame. So upon the evaporation, the molecule is dissociated into its constituent atoms, and this is called thermal dissociation of the molecules or thermal dissociation of the salt in the gaseous state. So this is in the ground state. Upon the absorption of the heat or heat energy absorbed by the ground state or the constituent atom, metallic atom, and it gets excited, and this excited atom is quickly loses energy in the form of light, or which is coming back to its ground state, and this light emitted is having a specific wavelength, and this light is in the form of proton. So this light is important for us to determine the element which is present in the sample solution, how much element present in the sample solution. So this is a pictorial representation of the principle of the plane photometry. So it's very simple. We just need to aspiration of the sample solution into the flame. So upon the aspiration, so we have next step is evaporation in the flame takes place. So this gets into a metallic salt, and this metallic salt upon the thermal dissociation or because of the presence of heat, this is dissociated into its constituent atoms. So these constituent atoms in the plane absorbed heat energy and get excited to higher levels, and this higher level atomic state is quickly loses energy to come back to the ground state, and this energy in the form of light or photons, and this light is important. The intensity of light gives us the information about how much ions present in the how much metallic atom which is present in the given solution, and the wavelength of this light gives us the qualitative information what is the element which is present in the given solution. So this is the basic principle of the plane photometry. So we'll see the instrumentation here. So it's very simple. We just need to take the sample solution and then make it to mist or make it to aerosol. Once we have aerosol, and then make it to mix it with the fuel, and this fuel is introduced in the flame, and the remaining things we know. So we'll see one by one here. So here is a sample in the beaker, and here is a one part is nebulizer, and in this nebulizer is having a compressor. I can say it is air which is passing here through the compressor, and then this nebulizer is connected to mixing chamber. This mixing chamber is connected to fuel. So here in the mixing chamber, what is happening is sample is mixing with the fuel. So once this mixing with the fuel, this mixed fuel with the sample is introduced in the flame, and this flame becomes color. So you know how it is imparting color, and this color is passed, this radiations which are passed through the lens, and then monochromator, and this chromator is the outlet of this monochromator is passed into the filter, and this is comes into the detector and the meter. So we'll see it one by one. So air is passed here into the nebulizer through a compressor. Here is a compressor at a given pressure. So once we compress the air in the nebulizer, this causes reduced pressure at the tip in the atomizer. So because of this reduction in the pressure in the sample here in the capillary, what happens? This causes the solution to be sucked into the nebulizer. So because of the reduction in the pressure, so solution is sucked into the nebulizer. Here the solution mixes mixed with the air and sample converted into mist. Here the air which is coming through the compressor into the nebulizer, and this air and the sample is mixed in the nebulizer, and this is converted into fine particles that we can call it as a mist. So here we can see these are the fine particles. So these are called mist, or we can say finely divided droplets, and these finely divided droplets pass through the spoiler. This is the spoiler, and this spoiler, the function of the spoiler is the fine mist is passes through this spoiler. The bigger particles are not passing through the spoiler. The spoiler is filters the bigger particles, and it allows to pass through only uh, fine particles of the mist. So this is the function of the spoiler. So that's what this is, a spoiler, etc. We can call it as a connector having filters. Then finally the mist is a combination of the sample solution and the air. The mist mixes with the fuel. This is the fuel. Of course the fuel is required to burn the uh, flame. So here the fuel, the mist mixes with the fuel in a mixing chamber and passes into the flame. So this is pass into the flame of the burner and burns. So here it burns the mixture that contains mist and the fuel. So this burns. Once it burns, the radiations are emitted upon burning the mixture. The emitted radiations are passed through the lens, that we can say eyepiece lens, and then through the monochromator which splits the color of the flame into the spectrum. This monochromator splits the radiations into the flame, splits into the color of the flame as a spectrum. Once it splits the spectrum, we have a filter here. Filter allows only the radiations characteristics of the element under the test to pass through. The characteristic radiations finally falls on the detector, or I can say the photodetector, and this detector converts analytical signal into the electrical signal, which is a direct measure of the concentration of the element under the test. So we have the instrumentation here, very simple. We have a nebulizer where the air and the sample is mixed, and this converts this mixture of this sample and the air. This mixture converts into fine particles, or you can say aerosols or mist. So these mist is passed through the spoiler, and the mist is mixed with the fuel, and this mixture is allowed to pass through into the flame, and here the element present in the mixture imparts characteristics color to the flame, and this color which is imparting by the flame is passed through the lens, eyepiece lens, and this is again passed through the monochromator, which gives us the characteristic spectrum, which is again passed through the filter to get a characteristic color which can detect by the photodetector, and this is converted analytical signal into the electrical signal, which is a direct measure of the concentration of the analyte present in the sample solution. So this is about the instrumentation of the flame photometry. So we shall discuss more about this flame photometric applications and their advantages and disadvantages of this flame photometric method, or flame atomic emission spectroscopy, flame atomic spectroscopic technique for the determination of elements present in the sample, or metallic salts or metal atoms present in the sample. So this is all about the today's discussion. We will see the further details in the next video. Thank you.